Thanks everyone for coming. Today we have Jeroen Schillewaert from the University of Auckland. He's going to talk about constructing highly regular exponents from hyperbolic proximity.
Thank you very much, Becky, and thanks to the SMRI for hosting me for the past 3 weeks. It's been great to be here. So I'm going to discuss some joint work with my colleague Marston Conder, who's Matthew's father, who was speaking last week, Alex Lubotzky, who you probably know, and Francois Thilmany, who's a postdoc in Belgium. And we did this work just before the COVID lockdown started. So the origin of expander graphs. So in this talk, there will be like a lot of concepts which I may discuss, but not in great detail. But I also want to give some context and some history, but will at the expense of maybe not always going into detail. So they originate in the 1960s in a paper by Bashvin and Kolmogorov, although they were not called expander graphs that way. So they were interested in modeling the biological network. So in the brain, apparently the neurons are all on the side of the brain, and in the big thing in the center are the axons, which provide the connections. And they wanted to investigate why this is the configuration. And it turns out that they sort of discovered that random graphs are expanders, which I will come back to later. And also that expanders do not embed very well into balls in R3. And that actually the way that our brain is stored is the optimal way in which you can actually embed. So it's kind of quite neat. And what I mean by a thick graph embedding is that you need to say, well, these neurons and these axons, they will have a certain thickness, and you don't want them to go through one another, etc. So you need to model it that these things have some thickness to them. And this is later generalized by Gromov and Good in a long paper. And then one of the first uses of expander graphs was to model communication systems through graphs, and where you will assume that information will propagate along edges in a unit of time. And of course, there are two things at play here. If you want to have a network, you want that your information arrives reasonably quickly. So you want there to be quick transmission, but you don't want your network to be too expensive. And in the 1960s, that meant you didn't want to have too much copper. Maybe these days, not too much optical fiber. So the question is how you're going to do that. And of course, the best graph with respect to quick transmission is the complete graph. You connect everything to everything and can't do better than that. But that's not very cheap because the number of connections is going to grow quadratically with the number of vertices. So this quickly becomes expensive. So this gives some motivation to look at the class of graphs where this number of edges only is linear in the number of vertices. So for convenience, you can look at k regular graphs. So every vertex is connected to k other vertices, then you will get this many edges. And then something which is really important is that when you speak about expander graph, you are never talking about one individual graph. You're always talking about a family of graphs. If there's one thing you remember from this talk, that should be it. It's not about individual graphs, it's an entire family. And we will see why in a second. So I'll give you the definition of an expander graph. So a finite graph X is called an epsilon expander if this notion h of x, which is sometimes called the isoperimetric constant because it's some sort of analogous to something in differential geometry. What does this epsilon of x measure? Well, in your graph X, you can consider a subset of vertices V, and you want that this particular subset of vertices V is well connected to the rest of your graph. So you wouldn't want that there are some people and they are very badly connected to the rest of the world. So everybody needs to be reasonably well connected. How do you measure this? You say, well, I look at V, I can look at this so-called boundary. These are edges where one vertex is in V and one vertex is outside of V. This is sort of your connection from V to the rest. And you divide this by the size of this set V. Okay, so you want that there's a reasonable number. Here I take the min, you could also restrict to vertex sets of half the size and then just divide by V. You want that the ratio of the number of edges that go out over the number of vertices that is in the set is at least epsilon. So that gives a measure of good connection. And here you can see why I don't want to talk about an individual graph, because all connected finite graphs would be epsilon expanders. You just make epsilon smaller than, say, I think 2 over x or whatever. You can make epsilon very small. Then for a given graph, it will satisfy this definition. So the whole point is that you need to be able to find a family of graphs which all can use the same epsilon. That is the game. Okay, so let's look at 2 regular graphs. If you have a finite 2 regular graph, I mean, then you are a cycle. There are no others because you start and then at some point you need to close up, otherwise you will be infinite. Now, cycles are bad. If you think about a cycle, if you cut in one place, then you will have bad connections there already. So these cycles, this isoperimetric constant is going to go to 0 as n goes to infinity. So you cannot expect that the family of cycles will have this at least epsilon, right? Because you're going to go below any epsilon you like. So then a natural question is, do expanders actually exist? Well, they do, otherwise my talk would finish prematurely. And they were first named expanders in a paper by Pinsker in 1969. But as I said, it was later, as with many things, discovered that it had already been done in Russia, so a little bit earlier by Barstin and Kolmogorov. And so there's actually a huge discrepancy between 2 regular graphs and k regular graphs for k at least 3. Namely, 2 regular graphs, there are none. And for k at least 3, the proportion of k regular graphs on n vertices such that this hx of n is less than a given epsilon tends to 0. So more informally, this says that random graphs are expanders. So a random graph, it will be an expander. Of course, if you're a computer scientist, you would say, well, it's all good and well that you tell me that they exist, but can you actually please give me one? And that took another couple of years. And it was first done by Margulis using Kazhdan property T. I mean, this property is not of importance for the rest of the talk, but this is one of the world's greatest mathematicians using very advanced machinery. So it was difficult to actually construct these explicit examples. And Margulis discovered this because at the time he was working in an institute for information transmission. So maybe he was tasked with finding these. Then we are going to be interested in this talk in highly regular expanders. So this is motivated by probabilistically checkable proof theory, of which I don't know anything, but I think maybe Murray knows and Yu-Ming probably knows a thing or two about this. But they have been studied by very serious people in theoretical computer science, Lassie Babai, Erik Dunur, Avi Richterson. And so the need for highly regular expanders sort of arose in their work. So what do I mean by highly regular expanders? Well, an expander by definition is a k regular graph, so every vertex is on k edges. Now I can ask that moreover, if I look at, let's say, an edge, I want that the number of triangles on an edge is also a fixed number, A1. And then I can ask, oh, maybe the number of pyramids on a triangle is a constant number, A2, etc. So if I can do that up to a certain level, I will call my graph highly regular of level n. And of course, I want these numbers to be non-zero, otherwise you could achieve high regularity very easily, right? So that's...
Can I take a comment?
Yes.
So there's someone in the computer science department called Penal in Sydney who's very interested in expanding. And it's very interesting from his point of view because the idea, so my understanding is that in computer science, you can think about, for example, memory or time as a resource.
Yes.
But also you think about randomness as a resource. So, you know, you have access, for example, to the internet that produces some randomness, you have access to the user moving the mouse, whatever. But in a lot of algorithms, randomness is restricted. And you can use expander graphs to like beef up your randomness.
Okay.
And so one of the things that I love about that fact is that we know that random graphs are going to be expanders, but somehow you're not allowed to use randomness to generate things you want to generate randomness.
Oh, that's interesting.
So that's why it's so powerful to have deterministic algorithm for expanders.
Oh, nice. That's interesting. If you missed it, Jordi made a very interesting comment. But, Okay, connectivity in the links. So that's the last thing that we will want. So for this application in PCT theory, you also want that your links remain connected. What do I mean by that? If I look at the vertex V here in this graph, this vertex V has 3 edges on it. And so in the link, you will just identify these vertices. These edges will become vertices in the link. Okay. And then you will connect them in the link if they were originally in a triangle. So here E1 and E2 were in a triangle. So I connect them. E3 is here by itself. It's not in a triangle with E2 or with E1. So the link here has become disconnected. We don't want that to happen. We want the link to remain connected. And these sort of prismatic examples will show up later in the talk. And so if we have a graph which is highly regular and connected, we will call it a highly regular connected. So Chapman-Linial-Peled were the first ones to look at this question of Dinur, and they studied highly regular expanded graphs of level 2. So level 2 is it's K regular and the number of triangles on an edge is a constant. And they asked the question, can you do better than level 2? So in particular, can you do level 3? And we will question this answer affirmatively. And then as things often go, sort of the same week as we were done, Fritgood and Illouz also could do this. But their methods are completely different. So as you will see, our methods, we sort of get the symmetry from the geometry, from the Coxeter polytopes, etc. And then we work reasonably hard to prove expansion. They said sort of get expansion quite quickly by using combinatorial methods, and then they use a symmetrization trick. So they make something which is an expander, and then they say, oh, now we're going to do some operations with it that keep the expansion and make it symmetric. So completely different methods, but also done. Regularity and connectivity, these depend on the particular Coxeter diagrams. So it's very hard to write like a general theorem, like to get these numbers or something. You sort of actually have to sit down and look at the diagrams in detail to get the numbers. Expansion is going to come from superapproximation. So I'm going to swipe this under the rug. This is a big hammer that we use in the end. Very complicated mathematics that will guarantee us the expansion, but we use it as a black box. Okay, so here, some of my slides will be more technical than what I say, because I don't want to write like sort of vague or incorrect statements, but often what is on this slide is not so difficult. So what is the first place to look at something where the number of triangles on an edge is a constant, the number of pyramids on a triangle is a constant? Well, a simplex by definition has these sort of properties. So simplexes will be the first place you want to look at. So if you have a polytope, so a polytope is one of these things, it's an abstract polytope for us. I will sort of assume that you intuitively have some understanding what a polytope is. And we assume that there is one K face, which is a simplex. And then we suppose that the automorphism group acts transitively on I faces. Well, then it's not so surprising that if you take the minimum of K and N, you will get a highly connected regular graph, because I said there is one face which is a simplex, and then by transitivity, all these faces. So this is an easy way to get highly regular graphs. So we will get one example that belongs to this class, which will be of level 4. But then we will have to look at a wider class to do better. So Coxeter systems, I know many of you here know this way better than I do, but for those that don't, I quickly repeat it. So we have a finitely, for us it will be finitely generated group W by some set S, which consists of reflections. And there are some relationships, ST to the MST is equal to 1. And Titz proved in 1961 that if you have a string Coxeter system, this is a Coxeter system for which if you write down the diagram, it's just a straight path, like no double bonds, etc. Then you can associate a so-called universal polytope, which is regular, and for which the automorphism group is the group that you started with. So that will be sort of the idea. We will have a Coxeter group, and it will act on some sort of a polytope as the automorphism group. Then there's a geometric representation of a Coxeter group. So in the end, we will use these black blocks of superapproximation. And for this, we will need something which lives in GL. So we will need to have a mechanism to get to GL. And the way to do that is we define a bilinear form between vectors ES and EP as minus the cosine of pi over MST. And then the geometric representation of W on V is defined by you send V to V minus 2 times this bilinear form times ES. So this is just the general version of what you teach your students in first year linear algebra class. If you reflect, you need to subtract 2 times the orthogonal components of this vector. And so this gives a representation of W into GLV, and this shows that this representation is faithful, and in fact, because we have reflections, it ends up in the orthogonal group. And so what will be important for us later is that I will want hyperbolic Coxeter groups. So I will want them, the signature, I will have to have pluses and minuses. Okay. So let's look at an example, spherical example from the cube. So here we have the cube, and we can look at reflections generated in this hyperplane, then that one, and this one. I hope you can see the pointer, otherwise it doesn't make sense what I'm saying. And then you can look at these relationships. So this gives you this digging diagram, and this is a so-called spherical Coxeter complex. So spherical because you could radially project from the center onto a ball. So these will not be good for us later on. I will need hyperbolic ones, but I mean, just to fix our thoughts. Okay, then a Euclidean Coxeter complex. We won't use these ones either. So you might say, oh, why are you showing all these ones that we won't use? But these are the easiest to illustrate sort of the ideas. Here, the W is generated by 3 reflections in this axis, this axis, and that axis. And so you have the base style X, and then as you reflect, you go out, and this gives you this Coxeter group type A to tilde, and the so-called Coxeter complex is the equilateral triangle tessellation. So we won't use these groups either later on because they are virtually abelian and they are not good for expansion. Okay, this is the projection of the hexacosichoron. So I put the fancy name on there. Does anybody know what less fancy name for it is? So it's the 600 cell projected into 3 space, and I know that Jordi loves his quaternions, so you can construct this starting from quaternions. You get the sort of double cover of the automorphism group of the icosahedron, like it's related to this double cover of SO3 by SU2. You can then use unit quaternions to get this cell. Anyway, it will play a minor role later on, and the link in every vertex should be an icosahedron, but I have to admit I cannot see this on the picture. I took it from Wikipedia. I mean, I just trust that it's the 600 cell. So I told you, like, this slide has more information on it that I will use. This is the drawback if you, let's say, borrow a slide from somebody. I will only use the things on the corner points. So I will use the cube, the octahedron, and the cube octahedron. And they have to do with what I'm circling. So here I have circled the leftmost vertex. And this means that I look at this polytope and I will declare my vertices to be the vertices of this cube. Had I circled something else, like the third here in the bottom right, then what I would have done is I would have said that the midpoints of the faces are my vertices of my polytope. And had I decided to circle the middle one, then I would have taken the midpoints of the edges in the cube to be the vertices of my polytope. And you connect them in a natural way. I mean, you can set it up with its cone, blah, blah, blah. I don't want to go in these details. But so where I position my circle has to do with which vertices I select to be the vertices of my polytope. If you're more into buildings, you just decide which type you're going to call the vertices. Okay. And this will be important. We will put like a circle somewhere. And these are called Wythoffian polytopes. So they're a slightly wider class than the regular polytopes I mentioned before. So here's our main result. Let WS be a Coxeter system, and M is a subset of S. So for us, M will be typically a set of size 1. So that will be the node that I'm circling. I showed you on the previous slide, I circled it. then you get a polytope PWM associated to this Coxeter system. So I showed you for the cube there, according to which one I circled, I got different polytopes. So here this PWM, it depends on W and also on which node I have circled. You get some so-called Wythoffian polytope. If WS is indefinite, you also want your polytope to have finite vertex links. The polytope itself will have to be infinite because our goal will be to construct an infinite family of expander graphs by quotienting out from a given mother object, which is the infinite graph. So the infinite graph will be the one skeleton of this polytope. So just keep the vertices and the edges, forget everything else. And we will take quotients of this. But we want the vertex links themselves to be finite. In fact, we don't need that, but people would not be, well, we want finite graphs. So this construction also works otherwise, but to get the finite graphs, we want finite vertex links. And we want the one skeleton of this infinite polytope to have sufficient regularity properties. Okay. Then the trick later on will be to show that we don't destroy this regularity when we take a quotient. And then the conclusion is there exists an infinite collection of finite quotients of X by normal subgroups of W, which form a family of A0 up to AN regular expander graphs. Okay. So this theorem is sort of conditional. It already tells you that I have found such a polytope that has high regularity. So to find such a polytope, this is where you need to look at the specific Coxeter diagrams and like actually show that you can do this. And then here, illustrating the main theorem. So I just want to give you some feel for like what kind of objects we get. So the first one is a 120-12-5-2 regular expander graph. So I'll elaborate a little bit more on that one later. But here I circled this one. And then the way you have to read this, if you look at the link of a vertex, it's just you delete that vertex and you put a circle around the next one. Like this is the theory of shadows, tells you that you can do that and it all works. And what you get here, if I take the link in this first one of this first vertex, you will get the hexacosichorum that I showed you before. If you take the link again, look at the end here, I have this thing. You get something with a 3 and a 5. This is an object who has it will be the icosahedron, sorry. So this will give us level 4. So we'll get a 120-12-5-2 regular expander graph from this one. By looking at families related to E8, you can get entire infinite families. And I put the word connected here. So in our construction, sometimes after a few steps, our things become disconnected. And so often we can do a little bit better than this, but then if it becomes disconnected, it's bad. For instance, look at this one. I start on the left, I take the link, I take the link, I take the link. If I take the link here, it will break into two pieces, this piece and that piece. Then you will get a prismatic construction like I showed you in the beginning that becomes disconnected. So that will be bad for answering their question of, and it's the same in this one. You can see here at this step, it breaks. So that's why I have to stop here. If I don't insist on this, I can add another number. And interestingly, like, I have to start here with 10 because I want hyperbolic Coxeter groups, and up to E8, it's spherical. E9 is Euclidean, so that's not good. That's why I need at least 10. A little bit more about the order 5-4 simplex honeycomb. So that's this one. It has this thing. The golden ratio is there. Why does the golden ratio show up? Well, because we are looking at pentagons, cosine 36, all that stuff has to do with the golden ratio. You can look at the number fields where you add phi to q, and then the matrix of the bilinear form, which I wrote down a few slides ago, will look like this. And so here you see it's quite concrete now. And you can see that the signature is 4-1 by doing some matrix manipulations. So this is a nice example. And you can look at the vectors for which the bilinear form is -1, and you will get 2 sheets, just like when you look at the hyperbolic quadric, it splits into 2 pieces. And basically, this thing comes from, I showed you like how we could tile the sphere with triangles, and then I showed you how you could tile the plane with triangles, where here we will have tessellated hyperbolic space by compact force impulses. So this is probably our most beautiful example, the 120-12-521. Can we do arbitrary high regularity levels? Yes, we can, but it will be, so we thought at some point that we had to answer their question for all levels, because they hadn't told us that they needed to stay connected in every step. Unfortunately, that has to be the case. And so this one is connected, except here in this step. When I go from, I look at the link here, I look at this, then in the next step, it will break into that one and that one. And it's quite interesting, this polytope, so the one skeleton is this thing with the middle vertex circled. What does this mean geometrically? Think about a simplex, but now instead of taking the vertices of the simplex, you take the midpoints of the edges. That's called a rectified simplex. And so here I would have a very long simplex, but I take the midpoints of the M faces in the two M faces. It's called a rectification. And interestingly, okay, you get these numbers out. That's not so hard to check. The one skeleton of this link here is called the Johnson graph. And that's interesting because the Johnson graph shows up in all kinds of areas of mathematics. For instance, in Lassie-Babai's proof of the graph isomorphism, this Johnson graph plays a crucial role. So it's kind of interesting that it shows up here as well. So we can get arbitrarily high regularity levels, but it becomes disconnected in this step. So groups and their Cayley graphs. So now I want to discuss the proof a little bit. So it will become a little bit more technical, but you will be able to understand at various levels. So first, Cayley graphs. So if you don't know what Cayley graph is, if you have a finitely generated group, you could put a graph down whose vertices are the elements of the group, and then you put edges if you can connect them with something in your generating set. And typically you want your generating set to be symmetric. So if you put A in there, you also put A inverse in there because you don't want a directed graph, you want an undirected graph. So for the free group generated by A and B, I can walk from 1 to A and then BA, BBA, etc. And this will be a tree because there's no relations there. And then another example is the Cayley graph. So you take the clock, and then I have three generators here, 2, 3, and 4. So 2 is the black lines, 3 are the blue lines, and 4 are the red lines. So it's modulo 12, and you just add up, you get a graph out of it. So we will use these Cayley graphs because Cayley graphs are a good mechanism to get families of expander graphs. So we will have a number theoretic construction which involves Cayley graphs, which is going to give us expanders. The most important part of the proof is the fact that we will have two things at play. We will have on the one hand polytopes, and I've already dwelled on quite a bit that from these polytopes we can get good regularity and good connectivity. On the other hand, I'm now going to look at Cayley graphs, and the Cayley graphs are going to give me expansion. And these two objects will be related, and it will be crucial that once I know that the Cayley graphs have expansion, that the polytopes have expansion as well. Otherwise, I won't have gained anything. And for that, I need the concept of a quasi-isometry. So what is a quasi-isometry? Well, it's something which is almost an isometry. So you're allowed to distort distances, but not by much. So for an isometry, the distance would have to be the same between xx prime and f of x prime. Here you're allowed to vary it, but you need to be able to find some constants a and b, such that this is required. Okay, why am I speaking about quasi-isometries? Well, because first of all, if you have a Cayley graph, there are often many different generating sets for a group. What we don't want is that if you choose one generating set and then I choose another one, that we cannot talk to each other. And these Cayley graphs are typically not isometric, but they are quasi-isometric. So it's the right sort of notion to speak about these objects. And then the second requirement of quasi-isometry is that it's almost surjective. So maybe not everything in the image, and maybe not everything in Y is in the image, but you will always be able to find something in the image which is not too far away. So if you have these two conditions, you have a quasi-isometry. And so here, this is a key lemma. We will make two families of graphs. On the one hand, it will be quotients of the polytope. On the other hand, it will be Cayley graphs. And we will show that the Cayley graphs are expanders and we need to know that the family of finite graphs coming from the polytopes are also expanders. This tells you that if you have two families, and you can find quasi-isometries between their respective members, such that the constants that you are using are independent of the member of the family. So I chose there a D because you can, and if you have an A, a B, and a C, you can just put a D, which is higher than all of them. You could write instead of D, A, B, C quasi-isometry. The point is, you want these constants here to be independent of the family member that you're looking at. Then this lemma will guarantee you that if one of them is an expanding family, then so is the other. This is a crucial observation. Yeah, this is surprisingly, like, took us a while to prove this. It's not very long, but it's tricky. I wouldn't recommend asking it on the exam. Okay, so I told you that we want to use this. So now I will need to first tell you that the Cayley graph of WS is going to be quasi-isometric to the infinite polytope. So that's the first step. I want the infinite mother objects to be quasi-isometric. And then the second step will be to show that this doesn't get destroyed when I pass two quotients. So why are these quasi-isometric? I illustrated it here with an example. So the Cayley graph here will be the dual of this Coxeter complex. So you take the midpoints of the triangles. And suppose I want to go from this one to that one. Then in the Cayley graph, I'll have to do a walk like this. And in the polytope, you can't see it, but these are like purple. These, maybe you can. These are red, and these are black. So in the polytope, you just take vertices of one type. And so the vertices of the polytope I have chosen here are of the red type. And they are at distance 1 in the polytope, because you connect two vertices in the polytope if they are in adjacent chambers and they are both the missing vertex. So the distance in the polytope here between those two red points is 1. And the distance in the Cayley graph is 1, 2, 3, 4, 5, 6. Okay, so it's not isometric. However, it is quasi-isometric. So because no matter what you do, you will only have to sort of like walk around the distance of the finite Wild group to get from one to the other. So this is the formal statement. You get a non-expansive quasi-isometry from the Cayley graph to the one skeleton of the polytope. So this is good news. We have a quasi-isometry on the level of the infinite graphs. Okay, so comparing quotients. So we assume now that the polytope has finite vertex links. And we denote a quotient map. So N will now be a normal subgroup of W. I will tell you later that these exist. And then I can look at the Cayley graph. I can quotient it out by N. And I can look at the Cayley graph of the projection. And the point of this commutative diagram at the bottom here, this is guaranteeing that for every such N, I get a quasi-isometry Fn between the finite graphs. And this commutative diagram guarantees me that I can do this with the same quasi-isometry constants as at the one on the top. So this tells me that the lemma that I showed you earlier is going to apply. I will have the same quasi-isometry constants. Okay. The details are not that important. I am now guaranteeing you that if I can prove that the Cayley graphs are expanding, then so will the polytopes. That's what you need to remember. Okay, regularity. It's all good and well that we have regular infinite polytopes, but what if after quotienting I destroy this? That would be really bad news. For instance, I had, let's say, 7 triangles on every edge, and now after quotienting I have sort of distorted that. It's no longer regular. All right, it's sufficient to have that after you quotient, it's injective on the neighborhood of any vertex. Then I will not mess up the regularity. And then secondly, I don't want to create new triangles, because if I create new triangles, I don't want that. And then these two conditions together, it's a small exercise to show that these guarantee that you will also not create new higher dimensional simplicities. That's just a matter of a little exercise. So if you have these two things, then you will be good. You will keep your regularity. Now, of course, not everything does that. You could have things that collapse. If let's say I have two neighbors of a vertex, I mean, it could be that I put them onto one another. So what you want is that your action of your normal subgroup N on the Cayley graph needs to have sufficiently large minimal displacement. You don't want to put vertices to other vertices which were not far away from them, because then you will destroy it. How far do you have to put it? Well, the moment you put it at least far away 4 away, you will not create new triangles, right? If it's 3, then you would have, I was looking for a pen, but there is none. So 3, and then if I would put these together, I will have created a triangle. But the moment everything is at least 4, that doesn't happen. But that's good. I want at least 4 in the action on X. By quasi-isometry, that means that I just need at least 5D plus 4 in the other action. Are there bad elements in W? Well, of course, but there's only finitely many of them. There are only finitely many elements in W that will not put you more than a given distance away. So we will just get rid of them. How do you obtain an infinite family? Well, this is by the theory of residually finite. So W is a residually finite group. What does that mean? For every non-trivial element, there will exist a finite quotient in which this element will remain non-trivial. So you can detect the fact that it's non-trivial in a finite quotient. In particular, this means there are lots of finite quotients, there's lots of normal subgroups. My whole strategy would fail if I didn't have normal subgroups, right? So basically this slide tells me that I can do that. Also, I want an infinite family of graphs. This is guaranteed by the fact that if you have a finite generated group, you can only have finitely many subgroups of a given finite index. And so if I take an infinite family, this index will have to grow, and hence the quotient will have to grow, so my vertices will tend to infinity. Okay. So many of these slides, if this is a bit technical for you, just remember I have now guaranteed you that like I have these normal subgroups, I will be able to find a big infinite family. Why do I need hyperbolic Coxeter groups? Well, because the other ones don't give me expansion. If the thing that I start with is a spherical Coxeter group, then it's finite. I mean, you cannot expect to get infinite family from a finite object. And if I started with the Euclidean one, it's virtually abelian, and these are well known not to lend themselves well to expansion phenomena. So you need the hyperbolic ones, otherwise it doesn't work. Okay, proof scheme of the main result. So basically, I've already sort of told you most of it, but it's good to remind you. We will have Cayley graphs, which are these quotients of these original groups that we started with, and they will form a family of expanders for an appropriate family of M's. This is where the magic of superapproximation is hidden as a black box. This is a major theorem by Alireza Salehi Golsefidi that tells you that such a family exists. So you can choose these things. I told you that the quotients you get quasi-isometries whose constants only depend on W and S. Since this is a family of expanders, my lemma then guarantees me that this is a family of expanders. Then you can say, aha, but you may have messed up regularity. But then I tell you, well, that only happens for short words. So I just make a new family where I get rid of those with short words, and it will still give me an infinite family. That's this I prime. And okay, now I have succeeded. These graphs have the regularity properties, and they form an infinite family of expanders. The big hammer is superapproximation. I can show you in the question time if you like. Yeah, the first bullet point. So you need to be able to say that you are going to take, you have your WS, your Cayley graph. You need to be able to say that you're going to find an infinite family of normal subgroups such that these quotient Cayley graphs are going to give you a family of expanders. So you need to say which ones you are going to choose. And that's incredibly difficult, but Alireza Salehi Golsefidi just tells you can take. I can show you, but it's my last slide of my backup slide, so I don't want to go all the way there and all the way back. But I can show you why I'm not discussing it. So I will finish on 2 open problems. So I have here some abbreviations. So now I have spoken about levels, highly regular connected level n, etc. So you can, these numbers that I have, they are n tuples of natural numbers. So a natural question is, well, which sort of n tuples can you achieve? I, for instance, achieved 120, 12, 5, 2. In these 4 regular, like, can you achieve, I don't know, 119, 37, 24? Like, okay, what kind of tuples can you achieve? So this highly regular connected is highly regular HR of n. That's just, you want one example of a highly regular graph of level n. HR infinity is you want infinitely many examples. HR exp is you want infinitely many which form an expanding family. And if I add a C, then I want all the things that I wanted before, and I want it to be connected as well. So that's the name of the game. So the question is, are any of these inclusions strict for n greater than 1? We don't know that. As an exercise, like what happens for n equals 1, that's an exercise. But it's an interesting exercise because you'll see a theorem we discussed. And then problem B, of course, as if problem A, we can't do problem A, so let's ask a much harder question. Let's ask, describe these sets as subsets of NN. So can you just give me which sets they are? This is a very hard question. For instance, knowing for which parameters A, B, you have graphs such that there are A edges on a vertex and B triangles on an edge, that's not known. Like it's, for instance, some guy had a paper showing that 7,4 cannot happen. And then I worked a little bit, you can extend this method, but it's very difficult to determine this. We have very sparse data points, and there are some obvious conditions, like everything needs to be at least one bigger than the next one. And then like, if you take the product of these consecutive ones, it needs to be divisible. I mean, you have like, if I give you 10 minutes, you'd be able to write down a couple of trivial conditions. And then if I give you another couple of days, you probably won't get much further. Like that's the sort of problem. There's a lot of fruit here. I just don't know how high it's hanging. But I think problem B is I would say, hopeless at this stage. I mean, so that I want to stop here. Thank you very much for your attention. Shall I show you the superapproximation? Salehi-Gossefidi tells you that you can get a family inside GLN0 of Z1 over Q0 by choosing primes like this. Okay, we use it as a black box. So now you might argue like, well, I don't believe that you can apply this result because you started with your bilinear form and then you ended up in an algebraic number field. But Salehi-Gossefidi is not in an algebraic number field. He's in a much, and for that we use Ray restriction of scalars. So you just like if you write something over C, you can write it as more equations over R. So you can do the same to pass from the number field into the rationals, and then you can clear denominators, and you can end up in this Z1 over Q. And then you need also some results by Benoit and de la Harpe that guarantees you that Salehi-Gossefidi's conditions are fulfilled. So I didn't want to make this a point of the talk because it's like, the thing is, this is quite advanced stuff, which we use as a black box in our setup, but it's a highly non-trivial.
So roughly the point that these subjects come from congruence.
Come from
congruence.
Yeah. It are well-chosen congruent subgroups, but this is about the extent of my knowledge about this result.
So they come up with different integer.
So as I said, they get expansion quite easily, and then they do this symmetrization procedure. But this tends to blow up their parameters. So no, they're very combinatorial methods, like think extremal combinatorics, that sort of thing. And so they can do better than us in the sense that they can do all levels and also remain connected at all levels. Perhaps the nice aspect of our approach is that our parameters are a lot smaller, and we sort of also, I mean, this is a matter of taste, but I would say that this is still reasonably explicit. We can still say what they are. Whereas there, it seems to be, it might also be my lack of understanding why I think that theirs is less explicit. I don't know. Yeah, they define new graph products, and then they say, okay, we already have something which expands, and then they do this procedure, and they prove that what they get in the end has these regularity properties. It's one of the many papers that I should read, but I haven't had time to read.
Somehow the point is that that theorem provides you an enormous supply of expansion, but you wouldn't be able to control the regularity. Is that the idea?
Yeah. So the whole idea of the proof is that like we have two sides. We have the geometric polytope side from where we get our regularity, and then we have this Cayley graph from which we get the expansion, and then the observation that they are quasi-isometric with the same constants allows us to conclude that the expansion transfers to the geometric side.
Thank you again.